So the first section we're going to look at this week is joint PMFs, or joint probability mass functions. And to do that, we'll just kind of jump in and let's assume that we have multiple random variables, and in this case, just two. And we'll call those a random variable x and a random variable y. And those random variables, x and y, both have probability mass functions, or PMFs, associated with them. So in this type of situation, we have a lot of information about x and a lot of information about y and the relative probabilities. If we go back to some of our previous discussions of discrete random variables, you can see that we have the ability to calculate an expected value of that random variable. We can look at the variance of that random variable, the probabilistic distribution of that random variable. There's lots of things that we've looked at as far as tools so far. But let's say that we're interested in finding more information about their interaction. So maybe we want to say, hey, what is the probability that the random variable x is equal to the random variable y? Maybe that's a thing that we wanted to figure out. And given these two individual random variables and their PMFs, we don't really have any information about how they interact with each other, about how they work together. And so in this section on joint PMFs, we're going to look at a way to do that. So the joint PMF is ultimately a probability mass function of multiple random variables. In this case, we'll look at an example here of two random variables where we have a probability mass function of the random variable x and of y. Both of those, again, being random variables. And we would say that this PMF is just equal to the probability that the random variable x is equal to a specific value, little x, and that the random variable y is equal to a specific value, little y. Again, should be pretty intuitive for this, but a joint PMF is just the probability of two random variables both being equal to unique but single valued functions. This sounds all good in terms of an equation, but what does this actually look like whenever we try and solve a problem with it? And so to do that, we'll bring up something that maybe looks a little familiar, and that's this, for lack of a better term, grid view, where we have a random variable y and a random variable x and values for each of those variables, the values 1 through 4 for each variable in this case. And this table right here, this grid, is actually a joint PMF when you look at it in terms of that. So we can go through and calculate, since we have values here for the probability of each interaction between, again, x and y, we have now the probability of each of those interactions occurring. And so we have this joint probability mass function, this thing that says here is what the probability is for every possible interaction of x and y. And as you can notice in this case, there's 16 unique possibilities or 16 unique possible interactions between x and y. And remember that a random variable has to cover all possible outcomes of that random variable. So there can't be a 5, 6, 7 here without extending this table for x to that extent. We can't add additional things to a random variable just because we want to. There actually has to be a defined random variable that is limited in scope, where we would say that the only possible values of x are 1, 2, 3, or 4, and that the only possible values of y, again, are 1, 2, 3, or 4. So with that in mind, let's take a look at maybe a couple examples. So let's say that we're interested in finding the probability mass function of x and y where little x is equal to 1 and little y is equal to 3. So to find this, all we have to do is go look at a very specific intersection. We've already got it defined for us as part of this probability mass function. And so that is the probability that x is equal to 1 and that y is equal to 3. So we find the intersection here, and what we found is that the probability mass function of x equal 1, y equal 3 is just 2 over 20. And you might be thinking, wait, that's it? And the answer is, yeah, that's pretty much it. Getting to this table is a little bit of a different story, but once you actually understand the joint PMF and have it developed, finding the probabilities of interacting random variables or the interactions between random variables is really, really simple. Now, let's say that we wanted to look at a slightly different question, and maybe that's the probability that x is equal to y, right? That's where we started out up here, was Maybe you want to know what happens where they're equal. Well, in this case, we're going to look at all of the areas or all of the cells where x is equal to y, and that's just this diagonal here. And we would sum all of those probability mass values up. So what we would end up with is 0 plus 1 over 20 plus another 1 over 20 plus 0. And so ultimately we would find that the probability that x is equal to y is equal to 2 out of 20, or 1/10. So 10%. Now, with that in mind, if you recall, we said for any random variable, the sum of the probabilities of that random variable has to equal 1. And the same applies for joint PMFs. And that is that the sum over all values of little x and over all values of little y of the probability mass function of x and y has to be equal to 1. Now, these values are going to be lower in each individual cell here than they would over just x alone or y alone. But again, when you sum over all possible probabilities of the random variable over that probability mass function, that has to be equal to 1. Now, let's look at this from a slightly different direction. And instead of saying we have two individual random variables, we use that to introduce the concept of a joint probability mass function. But let's assume now that we have a joint probability mass function. We already have this table here. And a question we might ask is, can we get the individual probability mass functions? So that, again, would be the probability mass function of x and the probability mass function of y. And the answer is yes, we can. So in order to calculate that, we need to introduce this concept of what's called a marginal PMF. And a marginal probability mass function, or marginal PMF, is just a PMF over one random variable when it's been extracted from a joint PMF. And it's really just the concept of a PMF that we introduced earlier. So to get this, we would look at the probability mass function, let's say of the random variable x, is just equal to the sum over all possible values of y of the probability mass function for the joint PMF of x and y. Now, we can also say this the other way and look at the marginal PMF for y, and it's very much the same, except now we would say that the probability mass function for the random variable y is equal to the sum over all x as opposed to all y as it was before. And again, it's just a probability mass function. So we're basically summing out the term that we're not interested in. We're going to sum over all x to find the marginal PMF for y, and we're going to sum over all y to find the marginal PMF of x. So looking at some specific examples here, what is the PMF of x for the little x4, right? What is that probability that the random variable x is equal to 4? And so in this case, we can very easily just say, okay, x equal 4 is this column here. And so we would sum over all values of y, which is going to be y equal to 1, y equal to 2, y equal 3, and y equal 4. So the sum over all possible values of y for x equal to 4 is going to be equal to 0 plus 1 over 20 plus 2 over 20 plus 0, which is equal to just 3 over 20. Now we can do the same thing for what is the PMF of y equal to 2. And again, we would look at this and say, okay, I'm interested in this row where y is equal to 2, and I would sum over all possible values of x. And so in this case, I have 0 plus 1 over 20 plus 3 over 20 plus 1 over 20. And so we can say that the PMF of y being equal to 2 is equal to 5 out of 20. So kind of summarizing, once we have a joint PMF, this PMF of x and y, given that we can extract a marginal PMF for just x on its own or y on its own, we can really get anything we want out of these random variables x and y. Another way to say that is that once we have the joint PMF, all the information we can get about x and y is already included in this table. So a joint PMF is a very powerful tool when it comes to working with multiple random variables. Now, the last thing we'll look at is extending to multiple random variables, and really more than two. So if we wanted to extend to, say, an x, a y, and a z, and we'll do it for just 3 in this situation, but the process is very much the same regardless of how many random variables you have. But we would say that the joint probability mass function for 3 random variables would be the PMF of x, y, and z for a given little x, little y, and little z. And that would be equal to the probability that the random variable x is equal to little x, that the random variable y is equal to little y, and that the random variable z is equal to little z. So very much the same type of thing that you would expect in this type of situation. Where things get a little bit weird is moving into marginal PMFs. So to get the marginal PMF of a single random variable, so let's say that's the marginal PMF of the random variable x, we would do a summation over 2 terms. So in this case, we would sum over both y and z to remove those terms from the joint PMF of x, y, and z. And thinking about it in those terms makes pretty good sense. It's just a way to say that the marginal PMF, you have to sum out every random variable that is not the random variable that you are interested in. And following from that logic, if you wanted to find a joint PMF that would be considered a marginal PMF of the original joint, so let's say this is the PMF of x and y, you would just sum out z. Again, the random variable z, where you would say that you're going to take the probability mass function, the joint PMF specifically of x, y, and z, you're going to sum out z, and you'll be left with the probability mass function of x and y. So summarizing again, once we have that joint PMF, we can sum over any random variables that we're not interested in to get a joint PMF of only the variables that we are interested in.